Hi everyone, welcome back to the channel. Today we're going to look at a few topics that I believe are crucial when developing Solana decentralized applications with, of course, the help of the Anchor framework. So first, we'll explore why byte level precision is so important in Solana development. Second, how to manage account types to avoid account types updates, of course, to avoid runtime errors and inconsistencies even, because I faced a tricky one, let's put it like that, and I want to share it with you so that you don't have to go through the same pains of figuring out how to fix it on your own. Number three, how to implement role-based access control using anchors, built-in constraints or attributes. So I'll give you plenty of examples of this. And finally, we'll wrap up with a comparison of Solana's decentralized wallet-based authentication and authorization, and how that compares to traditional sort of centralized identity platforms like Azure B2C, AWS Cognito, Google authentication, you name it. So there are plenty of centralized identity platforms out there that if you have been developing Web 2 applications, you know what I'm talking about. So we'll do just a quick comparison just to bring to life how much of a disruptive technology this is, because I think those industries are going to suffer as decentralized applications kind of become more prevalent. So let's get started. So first things first, why byte level precision matters. And this will tie into one of the things that I mentioned in my previous video, which is basically the space calculation for when you're creating, for instance, accounts in Solana, PDAs. You need to calculate the space they're going to take, because that will then result in a certain amount of rent that needs to be paid to the Solana blockchain to keep that account there permanently. So let's get started. So when developing on Solana, byte level precision, of course, is essential. Unlike modern programming languages that abstract away a lot of the memory management, Rust and Solana force you to calculate how much space your accounts will need down to the byte. It has been, in my opinion, quite a long time since many developers have had to kind of think about the size of the data types that they're using, and perhaps not since working with like lower level languages like C. And yet, working with Solana and Rust brings this concern back into focus. And what I want to do now is let's just break down why this matters and how it applies to both Rust and Solana. So, for example, as I say there on the third bullet point, a string in Rust takes about 24 bytes of fixed size just for the pointer, the length, and the capacity, kind of metadata associated with the type. And at a minimum, these 24 bytes are required to keep that data. A string can have, let's say, a length of 0 and a capacity of, say, 10, and meaning that it can store up to 10 characters before needing to reallocate more space. So if you're now adding the dynamic content, and you have like a very flexible structure, but very space sensitive structure, and this level of precision is necessary when you're allocating space for accounts in Solana, because if you don't allocate enough space, you'll start getting errors pretty quickly, and you will see that if you're not careful. So to refresh your memory, here's the purchase order data type that I shown in one of my previous videos. I believe it was video number 2 or 3. And as you can see here, this is the purchase order, right? There are several fields in here that are fixed size fields, like the unsigned ints or integers. For example, U8, the floating types as well, F32. Even the public key, for example, is a good example of a fixed size field. It's a vector, or it's an array, but it's a fixed size array of 32 bytes. So keep this in mind as we go into the next slide, because that will make a lot more sense. So just remember this when we go into the next slide. The other thing that I want to share with you, this is, sorry, my picture is kind of a little bit over what this is saying, but the point is that I wanted to bring to life one of the issues that I experienced when developing Solana programs is that when you're trying to, like, for example, in this case, this is the seeds to generate a PDA for a promotion account. Now, the promotion account takes all of these seeds, the promotion seed, which is a string. It takes a public key, which is the authority, i.e. the signer of the transaction. It also takes the supplier wallet address. So if the supplier has a certain promotion ongoing, then of course I use this supplier wallet. I didn't have to, but I decided to use it as the supply as one of the seeds. And finally, the last piece of data that is being used in the seed is the last promotion ID, right? And this one, if you remember, it comes from the admin account. So the admin account, as I believe I described this again in the last video, it has a bunch of stats. Some of those stats are counters for all of these accounts, data accounts in Solana. And of course, promotion is one of them. And I keep increasing. It's an index, basically, that I keep increasing every time I add a new account, so that next account comes along, it's just increased by one. So, and you can see this method here called 2LE bytes. And this LE stands for Little Indian, as I say here. And basically, this is the way that you convert in this case, an unsigned int of 2 bytes, 16 bits, to a byte array, which is basically in this format here, right? Trust me, if you try to use, the first one that I tried to use actually was not this one, was 2BE bytes, which is basically, or 2B bytes. And that one is I believe it's Big Indian. But anyway, avoid that one. That one gives you errors. The one that you want to use is this one. So I just thought about like sharing that little sort of hint, because it's all related to bytes sizes that we're using, etc., and converting things. So it's one of your biggest sources, and you'll see this in my next video when I start, or maybe in 2 videos time, when I start talking about serializing information to send from the client-side application to the server side, to the Solana blockchain, which is our server backend. A lot of the errors that you're going to experience are due to incorrect encoding or incorrect sort of conversion from your native data types to the byte array that you need to send. So let's go to the next slide now. All right, so another thing to remember is that in Solana, you need to explicitly calculate how much space an account will need. We talked about this already. And of course, this includes a fixed 8-byte overhead for the account itself and the dynamic size of fields like strings and arrays. So I have a formula that I used. I actually put that formula there. So space equals 8. We'll talk a lot more about this account metadata or account discriminator, whatever you want to call it, but we'll talk about this in a lot more depth when I start talking about the client-side code, the DApp client-side code, the Flutter code in my case. But just trust me that this is required. So 8 is always there, plus the size of the fixed elements plus the dynamic fields. So that's my formula, the formula that I've used successfully over and over again without any issues. So in this case, for example, you can see, so this is the space calculation for the purchase order that you saw on the previous slide. And as you can see, what I'm doing here is I'm calculating the size of the fixed elements of the struct first. Then I'm adding, and this, when I do this, this includes all the fields like integers and booleans if you have them, and the public key, all of the fields that are fixed size, they are already accounted for in this element here, in the size of this element. What size of doesn't account for are these elements here that you see. So it doesn't account for the strings. So you need to obviously calculate the number of bytes of each of the strings. So that's what I'm doing here. It doesn't account for the arrays of dynamic size. So promotion IDs is one example of that. So again, what I'm doing here is, how many elements does the array have? And then times, in this case, it's an array of integers, so 2-byte integers. So that's why I'm multiplying that by U16, or the size of U16. And then I have another array here. It's another example. So this one is actually a little bit more complex. So it's an array of selected products. And sorry, again, my face here is in front of it. But the point is, this is a struct type that has fixed elements. And as you can see here, so all I have to do is basically say number of products in the array times the size of the selected product. Simple, right? And then finally I have 88 because this is, I added a transaction ID as one of the fields that I would be using as part of the purchase order. I'm still not sure if I want to keep this. I'll probably remove it, and I'll explain in my upcoming videos why I will probably remove it. Because initially I was like thinking, yes, I'm gonna have this there, but I think I have now a good enough reason for not needing this, and there again, saving space and being more economical, and obviously this translates into less cost as well. So that's that. So this is obviously, as I said, this is one of the more complex sort of space calculations, but I thought, let me give you an example of a slightly larger one, so that at least you get a good sense for how to calculate space for accounts. So, and as you can see here, it's using a bunch of stuff in here that we're going to talk about in a minute, like all of these anchor attributes. They are really relevant because init is used for creating an account. Seeds, of course, is to derive the address of the account. Bump, I'm not going to go into a lot of detail on this, but just remember, this is effectively a way for the algorithm to avoid clashes with existing addresses. So it kind of increments a number to make sure that you never get like a duplicate address that is already being used. Then you have payer authority and space. So all of these things are the things that we're going to go into in the next few slides. All right. So next one. Right. So now we're going to switch gears very quickly. Just a brief stop at things to avoid. So I made a mistake when I was developing my my Solana contract, and one of the things that I did was this. So when you update account types in Solana, you must be careful to manage consistency. So adding new fields to an account can cause errors when old accounts still use the outdated structure. So this can result obviously in runtime errors like the one that I have there in red, which is basically trying to access beyond buffer length when you're trying to fetch accounts. And this is an error that I found while I was testing in the Solana playground. But it doesn't have to be the playground. It can be any client, like any application, even your custom custom decentralized application code. So your client could be fetching accounts and then trying to obviously deserialize them and turn the bytes array into the native types that you use in your decentralized app. Could be JavaScript, or could be Flutter, could be whatever you use, whatever technology you use. And the problem is that now you have inconsistencies. So I'll give you an example that I don't know if this was probably one of the examples where I ran into this issue. So imagine that you have like a customer record that you've defined in your Solana program. Later on, you decide that, like, initially you didn't have this field, but later on you decide that you want to have the encrypted shipping details field in there. So when you do this, when you add that field in, right, and you start, obviously you upgrade your program and you start creating those new accounts with that additional field. The problem is that when your DApp is now going to try and retrieve, fetch all of these account types of this particular type that you updated, they will have some accounts that have this field and some accounts that don't. And that's where you encounter the problem, right? So how do you fix this problem? So here's the solution. So this solution basically means that to avoid these types of errors, inconsistencies in account mismatch types in your blockchain, in your Solana blockchain program, it's essential to close the accounts, the old accounts, before upgrading your program. So this was what worked for me. So this means that tools like the Solana Playground or your own application, your own client, they don't encounter this mismatched sort of structures. So the short sort of step-by-step solution is close the old accounts, upgrade the program, then create the new accounts using the updated structure with the new fields that you added or removed, it doesn't matter. And then finally, now when you try and fetch, all is well again, because there is no type mismatch. Like, all accounts share the same type. That's it. Very simple. Just wanted to share this, brief, painful experience that I had, because it's obvious, obviously. And when I was updating the type, I was already kind of thinking ahead, and I was like thinking, I'm going to get into trouble with this. But I just want to see how, what's the reaction? Like, how is this going to react? Like, how is this going to work? And I was 99% sure this is going to be a problem, but I didn't know for sure. And then, bam, I encountered the problem. And then this was the way that I kind of fixed the problem. Right, so now we're going to talk about the exciting stuff of this video, which in my opinion is the security aspects of it. And I know, before you say, oh, security boring. No, this is actually super, super important. But it's not as painful to implement as in a Web 2 counterpart. Like, trust me, when you go through this at the end, you'll say, actually, this is not as bad as I thought it would be, at least comparing with Web 2. I'm always doing these comparisons because I believe that most of you that are watching this video, that you're already a very experienced software engineer, kind of used to developing these applications in Web 2, and now you're transitioning into Web 3, and you're kind of trying to draw the parallels between the two worlds. And this is why I find it useful to kind of draw these parallels, because it also helps you understand the massive benefits that decentralized applications have over traditional applications. And this is one of the ways that you have to convince if you work for a big company and they are somehow resistant to really truly embracing a Web3 or the Web3 conversion, and rely more on, let's just recycle the existing Web2 apps and just, buy off-the-shelf components that you're going to still be paying expensive fees to other third parties to just try and integrate your existing Web 2 with components of Web 3 that you still keep paying for. Actually, if you think about a re-architecting of your existing application, you will probably find out that you can save a ton of costs, and you can do it in a much slicker way. But anyway, off my soapbox. Let's just continue. So, role-based access control in Solana. So in Solana, we handle authentication and authorization using wallets and on-chain logic. Unlike Web2 systems that rely on complex and expensive centralized identity management, as I was just saying, Anchor provides constraints like has one and address to enforce role-based access control at the account level and relationships between accounts as well. The has one, for instance, is exactly that. So before we sort of dive into specific examples, which I'm going to provide, let's just examine the constraints definitions, and I will call out the ones that I've used before from the list as we go through it. And I'm not going to, because I don't want this to turn into a video as long as the last one, even though there is nothing wrong with that. It's just, I'll try to keep it as short as possible and straight to the point as possible. And so I'm not going to spend too long on the ones that I've not used, because even because I've not used them, I don't have that much experience with them. So I don't want to make any massive assumptions kind of trying to describe them. So I'm just going to call out the ones and spend a little bit more time on the ones that I've actually used and have experience with using, so I know how they work. So from this list here, I've used the top, all of them, maybe obviously with the exception of this, the last one, which is the init if needed. And that's, there is a big disclaimer there. You can read it on the slide anyway, but I'm not going to touch on that one. There are some, extra, if you're going to use that, you're going to have to apply some extra care when using that, but I've not used it, so I'm not going to talk about it. So you have NUT. So this obviously verifies that the account is mutable. So as you can see here, when you have this definition in, this attribute in the account, this has to match your client side. So again, probably either in the next video or on the video after that, I'll show you exactly what this means, how this ties back to the client side code. But effectively, just assume for now that what this means is when you send accounts, the list of accounts that you send to the instruction when you call from the client side, they will have to specify whether the account is writable or not, or mutable or not, and this basically means that Anchor is also going to verify that the account is mutable when it receives it. Okay? So very simple. Rule of thumb is, do I need to update the account in any way, shape, or form? If yes, then you need to specify it as a mutable account. Then you have signer. Obviously, you're going to pretty much use this all the time in every struct, in every context struct for your instructions. You'll always have one account which is the sign, at least one account that is the signer. So you verify that the account, verifies that the account signed the transaction. Again, Anchor does this for you. So it verifies that the signature is valid and it was the signature of that associated with that public key. Then you have a very important one. So I was actually pointing to this when we were talking about the promotion, I believe, the promotion structure. And as you can see here, so again, you have the init, which basically tells Anchor that you're creating a new PDA. You have the payer, so who's the person that is gonna, or the entity, let's say, that is going to pay for transaction fees and rent for the account, because again, without paying the full rent, you're not going to be allowed to continue indefinitely. Or let's put it this way, there is a small amount of rent that you need to pay every time, so you need to pay enough to be rent exempt. But anyway, I'm not going to go into the more details on rent just yet. And then you have space. Again, we talked about this when we were talking about the byte size, the byte level precision. So space is obviously the way that you tell the framework and you tell, what's your prediction about like how much space you're going to need to actually create this PDA, program derived account in or address in the blockchain. So you can read this at your own leisure. I'll include the link into this in the video description. So here you have other constraints. So which ones have I used? So I've used that one. I've used the seeds and bump, of course. I've used the has one. I've used the address. The only one I've not used is the owner. So seeds and bump, we've talked about this already, but this is basically used when you're deriving a new address to store the new account. Then you have has one. So verifies the account specified as has a field on the account equal to the key of the specified account to the name. So in this case, in this example, data.authority must be the same as authority.key. We'll go into a specific example of this in my next few slides. But this is a really important one because it creates a relationship between two of the accounts in the context received for the instruction. Address, this is super important and it's one that I used extensively in my code. So verifies that the account key matches the past public key. Again, I'll show you a specific example of this. Owner, I've not used, but as you can see here, I think this example is quite explicit. Easy to understand. So verifies that the account owner matches the past public key. So here in this example, they are basically saying, please make sure that the owner of this account here, which is my data, is the token program. Okay, so on this next set, so executable, I've not used this one. Rent exempt, I've not used that. Zero, not used that. Close, yes, I've used this one. So this is to close existing accounts. So this is an interesting one. So marks the account as closed at the end of the instruction and sends its LAN ports to the specified account, which is the receiver. So again, I think I have an example of this in the next few slides, but effectively this is a way to say you can close the account, and if there are any LAN ports left after closing the account, please transfer them back to whoever you specify there. And the constraint is also another one that I've used extensively in my code. And effectively, as the one-liner here says, verifies whether the given expression evaluates true. So again, I have examples of this in the code, so let's not waste any more time. The final one that I have for today is reallocation or realloc. So I have also a good example of this, so let's not waste any more time. But effectively what this does is, if you want to increase or decrease effectively change the space allocated to your account after already creating it, then you have to use this reallocate attribute so that you can change that size. That's it, that's simple as that. And here is what I was talking about. So this is a good example, right? So what this is doing is, this is my update customer context struct. So I have an instruction, and the instruction contains, obviously it has a context, which is the first argument, as I explained in my last video, has a context. The context for this particular update customer instruction will contain a context, and the context will have a link, or the context is associated with this update customer struct, which specifies the accounts that the instruction to update the customer is going to receive, right? And one of the other things you'll see here is the instruction shipping details encrypted, which is a field of type string. So what this basically, what you should assume from this is the instruction. I'm not showing you the instruction here, the definition of the instruction here, but effectively what this is saying is the instruction also has an argument over and above the first one, which is the context struct of type update customer. Apart from that, it also has at least one more field. It could have more arguments, but at least it has one more argument, which is the shipping details encrypted, which is basically the encrypted shipping details received from the client application. So as you can see here, there are several accounts being mentioned. There is the signer authority, there is the admin profile, there is the customer account, and then there is the system program, right? Let's talk about the one in this particular example that actually makes a lot of sense talking about it, is this one here. So because I'm updating the customer account, what I need to do, and I'm updating it, why? Let's just explain why this is happening. This is happening because the way the app works, if you remember one of my previous videos, not the last one, but the one before last, I believe, or actually the last one, sorry, my memory is failing me. So anyway, in that presentation, in the last video, I basically gave you a presentation of a demo of the client-side application, the Flutter application, in an Android sort of emulator, if you remember that. One of the things I said in that demo, oh, and by the way, just for to set the record straight, one of the things I said in that demo, I didn't remember at the time, didn't click in my head, and when I rewatched the video, and I was like, this is why. So let me set the record straight. So when I was doing the demo in my last video, there was a point in there where the account had not placed an order before, so it didn't have a history of placing orders. So at that point, the application didn't have a record of the shipping details to send the order to. So it asked the customer to enter the shipping details. So the customer enters the shipping details. In my case, I was demoing that for you in the video. And then at that point, I completely forgot that there was this call to update the customer, which is exactly this one here. So I completely forgot about that. I thought that after entering the shipping details, I would go straight into the order confirmation screen with the summary of the order, and then I would click the button one final time to get the order placed. What I forgot was that it would call this update customer. And at the time I thought, that's strange, that's weird. Why is it asking me to approve something and then show? So in my head, I was jumping ahead one step. I was basically just going straight to place the order, confirm the order on the blockchain, and that's it, job done. But no, I had forgotten. So it wasn't a bug. It wasn't an issue with Phantom. It wasn't an issue with anything. So it was working as designed. And the issue was that I forgot this step. So when the customer has not provided a shipping address, the app requests for the shipping address. But before it goes and it shows you the order details or the final summary of the order before you kind of confirm that you want to go ahead, it needs to update the blockchain with the shipping details. So I made a design decision at the time, which was instead of saving the encrypted shipping details in all the purchase orders, I want to save them in the customer account, which makes a lot more sense because I only save it once and it's there. And so it saves a lot of space as well, because this is not going to be a small field. It's going to be quite large. And it would be like if the customer places 10 orders, it's wasteful to save the same amount of space 10 times, for example, or X amount of times. So anyway, the point is I made a design choice to actually update the customer, not the purchase order. And so what that means is when I create the customer profile the first time, you remember, I believe, when you create the account the first time, and this happens when you download the app for the first time, you don't have a profile, instead of showing you the products, it has like a button there to say create the account. I click the button and then I create the profile. But when the profile is created, there is no shipping details because I prefer to delay requesting details that I don't need until such point in time that they're relevant. That's, I think, again, another design choice, but I made the choice like that because I don't want people to get bogged down providing too much information up front. I just enter the information as and when needed. If not needed, then there is no point in asking for those details, right? So anyway, that's why. So the user profile PDA gets created the first time without shipping details. And then the first time they place the order, then the shipping details are obviously going to be required. And at that point, I need to update the customer account before I place the order. And hence why we saw that confirmation as working as designed, where the app sent the update customer, called the update customer instruction in my Solana smart contract. It received these accounts that you see here on the screen, and it made a reallocation of space. Because why? Because now I have shipping details encrypted, which is a blob of data that is going to take, X number of bytes, and we need to reallocate space to account for this extra piece of data that now needs to be stored. And this is how you do it. So you have here the calculation of the space required. So again, 8, which is account discriminator, plus the size of customer, which accounts for all the fixed size in terms of bytes data attributes or data sort of fields that belong to the customer struct, plus the shipping details encrypted, which is the new piece that is going to be saved, dot length, because we want to know, how big is this string that is being saved. And then as you can see here, you also have the payer. So in this case, it's the authority. So I'm saying it's the customer that pays for it. And then you have 0 false, which I believe means that I'm not asking Anchor to 0 initialize the new space. So I'm just saying, just allocate the space, but I don't need it initialized. Yeah, that's it. Sorry, it was a long explanation, but I just wanted to make sure, like, set the record straight on the previous video, which is not the important part. The important part is explaining the logic of the app, which might be useful for you because in your application, you may have a different use case. But in my application, I made some, as you can see, some design choices to avoid asking for too much information up front, because typically that puts people off. Like if I get asked for a lot of personal details, like addresses and things, when I don't see a point or a reason to, especially in a decentralized application context, like a lot of the people that use these applications typically are very savvy, and kind of the ethos is I don't want to provide personal details if I don't have to. Of course, when you place an order for something that you want to receive, then of course, in that sense, in that context, it makes sense to ask for these details, and that's what I did. But anyway, the point is, if you have a use case in your application in the future where you are going to have a user profile, doesn't matter what type of application, could be something completely different from my own application. But the point is, you might have situations like this where you have an account, and now you're providing extra information to store in that same account, and this is how you do it. You use this realloc sort of action. Let's look now at 2 specific examples of applying all of these anchor attributes to our structs in our e-commerce platform. So the first one is this account deletion. As you can see, this is remove customer. So this is going to be called, probably, I'm still deciding whether this is going to be the case, but probably it's going to be a button that I'm going to create in the Flutter application, in the client side of the decentralized application, to enable the customer to actually remove their own account if they don't want to continue using the application anymore. And this would effectively delete all of their data, even though the data that we keep is very little data in there. So it's only basically the wallet address and a piece of encrypted information there, which is the shipping address for the purchase order to be sent to the customer. That is the bare minimum that we could keep. But even then, if the customer wants to close the account, then I'm probably going to allow them to do that. The only consideration here is, again, if you have ongoing, let's say, purchase orders. Let's say the customer just placed an order and the order has not been delivered yet. In that situation, I might want to not allow that to happen, or if he clicks the button, basically give him a message to say, wait for the last purchase order to arrive, and once that is done, click again, and then you can delete it, because having a purchase order that is not delivered and then not having the customer account kind of makes no sense to me. So to have like an orderly deletion of the account, we should ensure that all the ongoing purchase orders, if there are any, they should be closed off properly before actually allowing the customer account to be deleted. But in any case, this is like the only probably minor consideration that I need to give into implementing this functionality. So in this case, what you can see here is that you have a constraint being applied to the authority. So the authority here is the customer itself, himself or herself, and the customer here, the constraint is basically authority.key must be the same as the wallet address that is being passed in the instruction argument, right? So what that means is, this is basically a way to say, if I'm a customer, I cannot ask for someone else's account to be deleted. I can only ask for my own account to be deleted. That's it. So this is what that constraint is trying to do, is to say you can only ask for your own account to be deleted, no one else's. There are a few other things in here that I'm not going to spend too long on them, because I prefer to show you the next slide, which basically contains a much richer example of the application of these. This will be the same, and there will be situations there that are similar. This one actually does deserve to be called out. So what I'm trying to say here is that, obviously, as you can see, this account is mutable because it's going to be obviously to be closed. But I'm saying close equals authority. That means that when the account is closed, if there are any positive Lampert's sort of balance to be returned once the account is closed, then please send it back to the authority, which in this case would be the customer. So that's good. So you get some of your money back. So that money was obviously, those Lamperts were being used to keep the account rented exempt, i.e. for the account not to be closed off in the system. Yeah, so that's it. So that's all I wanted to say on this one. Next one. So this is the really, like, this slide is so busy, but let's just go through it in detail, because there is so much that Anchor is doing here for us that it's just unbelievable. So let's go one by one. So let me just go through my notes here in the slide, just so I don't forget to mention anything, because there is a lot happening. So the first things first is, as mentioned in my last video, when you define an account in Anchor using the sort of the account attribute that you see here, Anchor ensures that the account data is obviously serialized and deserialized correctly as part of reading from or writing to the Solana blockchain. So this is key. And it's something that is done automatically for you, as I mentioned before, and it's great because we don't have to do this explicitly. Great. Point number one. Point number two, again, we can see here that the size of the promotion struct is obviously being calculated using kind of the same formula as before. 8, that 8 is always there, the account discriminator that I mentioned we're going to talk about more when we talk about the client-side code, plus the fixed elements of the struct. So that's what this size of function is doing. It's basically calculating the size of all the fixed elements of the promotion struct, plus all of the dynamic ones. And you can see that there are plenty of arguments that are received. And these arguments are basically going to be then used to calculate the dynamic portion of the space calculation. Again, we talked, I'm repeating a little bit myself, but we've talked about this in the previous slides, the so-called space calculation. If the accounts aren't passed in the expected order or don't match the expected type, Anchor will throw an error before the program even runs, before the instruction even runs. And you will see this in your journey of implementing your own smart contract. I've seen it plenty of times. Trust me, you'll see it as well. So a lot of times, and this might cause some confusion to some because, as you've seen in my previous code walkthrough, I think in the previous video, I've shown you some instruction code, and you've seen that I had I was calling the macro to generate some logs saying, I just started this instruction and then at the end I just finished this instruction. And sometimes when you get the errors, you from the client side, you call the instruction and you're watching the logs, the log stream, and you don't see those errors come through, and you're like, why isn't the instruction even sort of executing? And the reason being is because it's failing even before the instruction even, the code of the instruction even starts, because Anchor is doing some magic behind the scenes, like deserializing your accounts and running some validations on your accounts, like is the account in the right, the accounts array that I received for the instruction in the context, is it in the same order? Like, is it the signer first, followed by the admin profile, followed by the promotion account, followed by the system program? Like, the accounts in that order. Can I deserialize and serialize them in other types, like the same types? Are the number of bytes that I'm expecting the same? Like, there is a ton of validations that are being done by Anchor that if any of those fails, it fails even before you get into the instruction itself. And that's why you sometimes don't see the log messages. That's because it failed even before the instruction started. So that's really important for you to understand. One of the things that I think I would like also to call out here, we talked about seeds so many times, but I don't think I mentioned this before, is that the seeds line, for instance, in the admin here, to instantiate the admin profile, they ensure that the admin account is derived from the correct seeds. So this validation ensures that the derived account matches the expected public key using the provided seed and authority. Anchor, of course, abstracts away the complexity of generating and verifying these seeds, but the point here being, and this is what I'm saying here on this point, number 6. Anchor validates that the seeds for admin generate an account matching the key of the received account. And I underline the word received. Why? Because say that I sent an account to impersonate the administrator on that second slot, and it's not the administrator itself, it would fail at many levels. First, when the seeds are generating the public key of the admin profile, and then that doesn't match what is received, that would trigger an issue right there and then, right? But even if that were to succeed, then it would fail on the next constraint here, which is the has one authority. Again, this is establishing a relationship between admin profile and the authority, the signer, and it's basically checking, as the point number 3 is stating here, that the admin profile.authority equals authority.key. So I'm establishing a relationship between the admin profile account and the authority account, and saying that they basically have to be the same. Otherwise, this should fail as well. So, yeah, so as you can see, that there is a ton of validations happening here. I don't think, did we talk about this one? So the address one is another good one. So what I'm saying here is only accept signers where the address equals the address of the admin public key, which obviously is hard-coded in the smart contract itself, in the same way that it's also hard-coded in the client application itself. So it's important that these, both the client side and the server side, that they both know what the admin's public key is, because it will be used for a multitude of different things, like generating seeds, generating addresses from seeds, and also, in this case, to validate that the account that is the signer is actually the administrator. So as you can see, some of these, let's say some of these checks, you might think that they are kind of overlapping, and they may be overlapping somewhat. Like, I might not need all of these checks because they essentially, for example, in this case, what I'm saying here is that if I know that the admin account was created by the administrator, right? What that means is that even if I didn't have that constraint there, this one should guarantee that no other entity other than the administrator can actually call this, because the account with the admin seed and the relationship between this key that was created before, if that was created by the rightful administrator, then this comparison saying that the admin profile.authority matches the authority.key. So if someone else was calling this, that would also fail, right? But again, I think this is important that, you have, the security is all about defensing layers, right? So if the outer layer fails, you should have an inner layer that tries to defend you. And if that inner layer fails, you have another inner layer. So it's almost like, the layers of an onion, if that's a good analogy. So you take one and there is another layer, you take another one, there is another layer, and so on. So there is no such thing as the perfect bulletproof system in IT security, because there is always a way to break every system. It's not so much about making the perfect system. It's more about making it as painful and as difficult as possible, so that if your system is so incredibly tough to crack, it might put off the attacker, because the attacker will say, well, it's just going to cost too many resources are going to be needed in order to crack the security on this system. I might just go to somewhere else, because there is much easier targets where I can get like the same reward, if not higher reward, with less effort. So this is the game, right? So this is And this is why, as I was saying here, it's so important to have all of these layers, because they all act sometimes in tandem with one another, but it's also because they complement each other sometimes. And yes, there may be a little bit of overlap. You might say, well, I don't need this because I have that. No, actually, if the relationship exists like this one, have it there. There is no problem in doing that. If if you know that you want only that address to be the signer, have it there as well. So this means that effectively, if someone else other than the admin is trying to call this, it will fail at multiple levels. Obviously, only one of the probably the anchor framework is done in such a way that is smart. So it's not going to validate all the conditions. If one of the conditions fails, it stops right there and then, because the first condition that fails means that the whole thing fails. So there is no point in continuing to check the other conditions. It's just economical in that sense that if the logic at the first one that there is a failed validation, the whole there is a cascading failure, and no one else. No, the code doesn't need to go any further because one of the security checks failed. So that's that. Sorry, I was rambling a little bit, but this is the key element here is that this slide has a ton of information in there, and I just wanted to again convey the message that Anchor does a lot of the heavy duty sort of lifting on this, but it's never enough to emphasize that. Right, so next one, let's go. Right, so the very last topic that I want to talk about is basically comparing Solana's wallet-based authentication to centralized identity platforms. And why did I want to do this? Because I'm sure that if you're a senior engineer, you probably must have worked in many projects during your experience where you had to deal with centralized identity platforms. And you know as well as I do that those platforms, if you're trying to roll out one of these centralized identity platforms in an organization, that's a big deal. It's painful. It takes time. It's a lot of people involved, a lot of money. And the money, when I'm talking money, I'm not just talking money about configuring the platform, because no platform, like no matter how much they tell you that it's only vanilla configuration, you're not going to need to do anything from a development point of view, that's BS. Most of the time, you do need custom development to fully integrate a centralized identity platform in your company's environment, IT environment. So most of the time, that is not insignificant. It's a very, very difficult project, and it's also a project that terrifies a lot of people in the senior sort of IT leadership, because guess what? If this is about authenticating and authorizing people to use your applications, imagine what would happen if you somehow misconfigure it or deliver it with some bug. That might become a news event, like the newspapers and TV channels and you name it. Media would have a filled day if your company is like a large organization that is doing these types of projects. It would become the talk of the town, because if your system is now stopping people from logging in and from being able to use the application, that would be terribly embarrassing. Your brand would be negatively impacted. Customers might just choose to go somewhere else and not use your services anymore. So it's that damaging. Brand reputational damage is a real thing, and these are the types of projects that typically result in that damage being done. Or just one example of those projects that can have a massive impact in the organization. And this is why I decided to make this comparison, because one of the key advantages of Solana's sort of decentralized approach is the use of wallet-based authentication. It's built in the system. It's part of the blockchain. There is no need for licensing fees or complex systems like implementing one of these centralized platforms like Azure B2C or AWS Cognito or Okta or you name it. There are so many out there. Google Authentication. There are so many out there. One of the things that I like about using decentralized applications, sort of native authentication approach with wallets, is that you eliminate immediately single points of failure in centralized systems. We've all heard the stories of centralized identity platforms that were breached, and then a whole raft of sensitive user data was leaked, and they were able to not only get access to that data, but also infiltrate the organization systems and do a lot of damage, right? So using decentralized applications, built-in authentication and authorization sort of mechanisms, using frameworks like Anchor, as we've just seen, result in a more secure and sort of cost-effective solution. Just to give you an idea, to replicate Solana's security using a centralized platform like Azure B2C, companies would need to deal with not just complex configurations and ongoing fees, as I just described, but for a company with just say, I imagine that for a company with Amazon level traffic, like a company that has millions of transactions any single day, for example, you're looking at, you could easily cost over 1 million per year just on fees that you have to pay to the third party to keep the system going. So, Solana's, and when I say Solana, any blockchain, this is not unique to Solana, but this wallet-based authentication eliminates a lot of this, not just from a cost perspective, but also, removes these single points of failure. And this is a more resilient, a better system. And this is why I love, this is one of the massive selling points. It's not the only one. This is definitely one of the biggest, in my opinion, is that if you, and this applies to both centralized applications and decentralized applications. If you do security well for both of them, you will be spending a lot less effort trying to achieve a secure application in a decentralized world compared to trying to do the same in a centralized world. That's what I'm saying. That's it. I think we've completed today's journey. Sorry, it was a really long one. I rambled a little bit here at the end, but hopefully you enjoyed what I had to tell you. I had a conclusion slide here, but I'm not going to labor this too much. This basically, is a list of all the things that we discussed. We talked about, why byte level precision is important. We talked about the account consistency. So, making sure that we close before we update the structs that we are using in our smart contract. If we're going to update them, we need to make sure that, that we don't end up with mismatched sort of types in the blockchain. I talked about, obviously, more than half of this presentation was talking about the anchors, security constraints, and how to apply them in our applications. So hopefully you enjoy that. That's one of the really, really important things. And, please do spend the time offline trying to learn this properly, because if you do implement these security constraints in your smart contract, that's a sure way to give yourself the confidence boost that your contract is going to perform well in production, but perform in a secure manner as well. And finally, the last point was just this, that we were just talking about, like comparing the Web 2 world with the Web 3 world, and, how I personally consider the decentralized application paradigm in terms of authentication and authorization way more secure, much easier to implement, reducing single points of failure, reducing massively the costs that you have to pay to pennies. And yeah, this was the content of today's video. So looking ahead very quickly, next video, I am going to start talking about the Flutter client development time. It was an interesting journey on the client side as well, and I want to share that with you. And I will start the next video talking a little bit about the architectural choices that I made while building the client decentralized application. And I spent a lot of time actually thinking about like how to architect this in such a way that makes it easy to maintain and update anytime I need to update it. So I'll spend a little bit of time talking about how, like, what were the architectural considerations that I had to consider before going ahead and like starting to type code, because initially I did a few prototypes, but I wasn't happy with how the code was sort of being organized, and the code felt a little bit cumbersome to update here and there. It didn't feel right. So in the next video, yeah, we'll start like going into the client side. So we spent like these first few videos sometime talking about the Solana smart contract. Now we're going to start talking about the client side. That's it. That's all I had to say for this video. Thank you very much for watching, and yeah, stay empowered, stay decentralized. Thank you very much.